We will now come back to multiple blocking, or to block, and specifically to blocking multiple variables. So let's say that we are interested in the pattern of variation over time of a constituent of blood. So this is the treatment that we are interested in. So the variable that whose variation we are mostly interested, and we need sampling blood from 9 chickens, and this is the first blocking variable on 25 weekly occasions. So only 6 samples can be analyzed at a time, and there can be a substantial difference between batches of the samples. So every week there can be important differences due to the weather, due to the whatever other reason. So this is the second blocking variable. So we can see that we need to block these two variables, which is the chicken and the batch, and we want to analyze this variation of the constituent of blood over time. So time is the treatment. So let's say that we are interested in the wearing performance of 4 tire brands. This is our treatment, and there can be differences depending on the car. So this is the first blocking variable that we don't want to interfere, and the second one is the position within the car. So maybe the wheels at the front, they wear differently from the wheels at the rear. So the organization of this experiment can be done through a Latin square design. So whenever you have two variables that have the same number of levels as the treatment, you can use a Latin square. So we have 4 treatments, 4 positions, and 4 cars. So you arrange the car and positions like this, and then you have to fill this matrix in such a way that each treatment appears on each row only once and in each column only once. So this is a Sudoku, and you can find it. Okay, so we may count the number of degrees of freedom. So we have 16 experiments or 16 observations, so we have 15 degrees of freedom. We need 3 for the treatments, 3 for the blocking, 3 for the first blockings, 3 for the second blocking, and we have the remaining for the errors. Because this is relatively low, 6 is relatively low, will give us very little power. We can repeat this experiment multiple times with independent Latin squares, and here you have a model or a web page to generate multiple Latin squares. So the Latin square is not unique, so there can be multiple Sudokus for the same combination or for the same number of treatments. They're not infinite either, so given a particular size, there is a particular number of possible Latin squares. So this one generates one randomly, and this is the analysis model. So it is just a main effect model, and if you have to repeat it, then you use a second set of wheels, a second set of tires, and you may use the same car, but you rearrange the brands. So now car 1 on the 5th occasion, that is equivalent to the first position. So the position is, you have front left, front right, rear left, rear right. So in the 5th occasion you will choose one of these 4, but you use a different Latin square to the one that you used in the first replicate of the experiment. Okay, so you may use different tires or different tires and different cars. So this blocking uh, can help to better assess what is the effect of the brands. And sometimes we may reuse the experimental units, and this is especially important in fruit trees, for instance, or agricultural plots, sometimes in patients in a clinical trial. And the solution is to use two orthogonal Latin squares. So we may have a Latin square with Latin letters. So we have A, D, B, C, and so on. And we may have another Latin square with now Greek letters. So you have alpha, beta, gamma, delta. You see alpha, theta, alpha, delta, gamma, and beta. And the reason to do this is that you may have an experiment, let's say, with a fruit tree to see what is the best way of fertilizing the tree to have a largest growth. And once the experiment is over, now you want to use a new fungicide to see also the health of the tree. But trees take a lot of time to grow, so you cannot throw the tree and start a new experiment with a new tree. So what you have to do is to make sure that the previous experiment does not interfere with the new one. So there is not a carryover from the first experiment to the second. And to do that, these Greco-Latin squares are very useful. If you look with attention, you see that every pair of the experiment 1 and experiment 2 treatments, they appear only once. So you have A alpha, B alpha, C alpha, and D alpha. And then you have, for instance, C beta, D beta, A beta, B beta. And the same happens with all of them. So that is the way that alpha is in all the levels of the experiment 1, and the same for all the other levels of the experiment 2. So that is the way to avoid that the first experiment is carrying over into the second. And we have explained it with two different time points. So first you do experiment 1 and then you do experiment 2, but you can do it also two experiments at the same time. So these two experiments can be carried out simultaneously, and you can do also this with animals. So you may use the animal for two different experiments that they don't interfere with each other. And here is also another interesting idea. These are called row and column designs, in which the number of levels of each one of the Latin squares can block two variables whose number of levels is equal between them and equal to the number of treatments. So we had 4 cars, 4 positions, and 4 tire brands. What happens if the number of levels of the blocking variables are not the same as the number of variables of the number of treatments of the treatment variable? And for that you may use these row and column designs. And for instance, if the number of rows or the column of all columns is equal to t, so we may use these Jordan squares. Okay, so let's say that one of the blocking variables is equal to t, but the other one is not. So you would start by designing a Latin square of the size of t, and then you choose 3 columns. You have to choose wisely. It is not that it doesn't matter which ones. So but yeah, so especially because we want the design to be balanced. And complicated patterns may appear. The number of rows and columns is not a multiple of the number of treatments, or some combinations of the blocks are invisible. So for instance, some plots in the field are useless. And in the design of rows and column designs, the goal should be to achieve orthogonality in each one of the blocking variables, and to choose balance if orthogonality is not possible. And if balance is not possible, then at least the joint occurrences of treatments in rows and columns should be made as equal as possible. So our first goal should be orthogonality, then if not, we should try to balance, and if not, we should try at least to make them as similar as possible. And here you have another example in which we have 9 treatments and we have 5 rows and 7 columns. So we have here the 5 rows, the 7 columns, and we have this design in which we try to make the experiment balance or orthogonal. And yeah, it is not easy. It requires mostly an algorithm to do that, but computers can do that, and these are called row and column designs if you look for them. And also here you have another example which we have block 1, block 2, and some of the combinations are useless. So let's say that this combination between block 1 and block 2, let's say this is an agricultural experiment, and this plot has become useless for whatever reason, then we may skip it, and the same for all these blank spaces. We may also block time, and this is the goal of crossover designs. Also we may block the animal, because we may apply a crossover design on the same animal and different parts of the animal. So you apply a treatment to the left leg and a different treatment to the right leg, and you assume that they don't communicate. Okay, so the idea is that the different treatments are applied in sequence to the experimental unit. So this sequence is talking mostly about time, and the aim is to use the same subject, because doing this will remove the intersubject variability. So one of the major sources of variability is that people are different or animals are different. Well, animals not so much, because they are genetic twins typically, but people are rather different. So if you can use the same person for both treatments, then you will gain a lot in statistical precision, and you will reduce also a lot the number of subjects. The design assumes that there is no effect from one period to the next, and this only happens for treatments that do not modify the nature of the patient. So what if the subject is cured by the first treatment, then the second one there is nothing to measure. So the experimental unit is redefined to be an observation of an individual subject. This is the first blocking variable in a short period of time. This is the second blocking variable. So we will have the different subjects and then the different periods. This is the blocking variable, and the subject too is also a blocking variable. And then we have the treatment, and these people are assigned randomly to each one of the sequences. So we have the first one will receive AB, the second one will receive BA, BA, AB, and so on. And if we are to use multiple sequences, why restricting ourselves to just 2 repetitions? Why not trying ABB or BAA? So we will be able to better measure the effect of B or A in each one of the patients. And we may expand it to all possible combinations, so ABB, BAA, ABEA, and so on. So we can be rather creative in the sequences that we can create. And the experiment, that is swapping treatment, so the same subject is subjected to two treatments or a sequence of treatments, is rather different from its future use, in which each patient will receive only one treatment. And you may expect some objections, and some of these objections, not some, they all make sense in their own context. So the first one is order effect. So it is possible that the order in which treatments are administered, they may affect the outcome. So an example might be a drug with many adverse effects. If it is the first one, then the patients taking a second but less harmful medicine are more sensitive to any adverse effect. So they have been hypersensitized. And there could be carryover effects. So it can be avoided if sufficiently long washout periods are considered, and the designs are specifically made to eliminate these first order, second order carryover effects. Actually, these two can be addressed from the statistical point of view. So when you analyze your data, you will be able to correctly attribute what is the effect of the order, what is the effect of the carryover. And the learning effect is important when because you have some controls that are naive to the internet therapy. So for instance, let's say that you are analyzing, or you are comparing the effect of yoga on stress and a given drug, and the first one of the groups first received the yoga sessions, and then the drug. The other ones drug and then yoga. But when the people are receiving drug after yoga, they don't forget about yoga. So it might be that you see a difference, and it is because of the first treatment. So this is a carryover effect, in which there is no way to do a long washout period. So if there are no carryover effects, these designs are like the row and column designs. If there are carryover effects, the design has to be performed to remove first order, so only from the treatment in the previous period, or higher order, so second order is from the two previous periods, so third order is from the 3 previous periods. And you can design the experiment to do this. We will see a little bit how to do that. A design is said to be uniform within sequences if each treatment appears the same number of times within each sequence. For instance, A and B or BA is uniform in sequence, but ABA or BAB is not, because here B appears twice while A appears only once. And the design is also said to be uniform within periods if each treatment appears the same number of times within each period. So this depends on the number of subjects assigned to each sequence. So going to here, it is within, so uniformity within sequence is analyzing by columns, while uniformity within periods is analyzing by rows. So by rows, A and B have to appear the same number of times, and within sequence, A and B have to appear the same number of times. That doesn't happen here, but it does happen in this one. Okay, and a design is balanced with respect to first order carryover effects if each treatment precedes any other treatment the same number of times. And Latin squares, although not all of them, help to construct these balanced designs. So for instance here, so let's say that we have 4 treatments and we have 4 periods, so we can have multiple sequences. So we design the Latin square, and this Latin square is giving us the sequences. So this is sequence ABCD, BCDA, and so on. But this design is not balanced. For instance, A goes before B in 3 of the occasions, so it is once here, twice, 3 times, but it does not precede C or D. So A just before C doesn't happen. Here is a different Latin square, and this time the design is balanced. So all pairs appears once. So you have A before B, A before C, A before D, and you also have B before C, B before D, and B before A. So this is a balanced design, the other one is not. And if the number of treatments is even, only one Latin square is needed to produce the balanced design. If the number of treatments is odd, then you need 2 Latin squares. Okay, so let's see. So here we have an example with an even number of treatments. Here we have it with an odd number of treatments. So we design we use a Latin square, we use a different Latin square, and now we have our sequences. And this design is balanced because all pairs appear 2 times. So let's see, we have AB, AB, and then we have AC, AC, and then BC, BC, and BA, BA, and so all pairs appear twice. A design is said to be strongly balanced with respect to first order carryover effects if each treatment precedes every other treatment, including itself, the same number of times. So what we have added is this strongly, and this strongly, for instance, these sequences, ABB or BAA, the design is strongly balanced, but it is not uniform within the sequences. So uniform within the sequences, so it was the treatment appear the same number of times, and strongly balanced means that each treatment precedes every other treatment the same number of times. So here we have AB once, BB also once, BA once, and AA once. And this design here, this design is strongly balanced and uniform within the sequences. So each treatment appears twice, and if we count the number of times that AB appears, appears before B, we have it once, 2, 3 times, and then BB we have once, 2, 3 times, and all pairs appear the same number of times. So we can design sequences with very nice properties. And let us analyze how these carryover effects can be washed out, why they are washed out. And to do that, we will use a very simple design. This is just this one, ABBA. Okay, so what are the expected values for each one of the cells here? So here we would have the response in the first period for this sequence will be a general mean plus something that depends on A plus something that depends on the order AB plus something that is the effect size of the period. So the period, the first period, is also contributing. And then in the second period, we will have a general mean plus something that depends on B, plus something that depends on the order, plus something that depends on the second period, plus the carryover effect from A to B, because we haven't respected this washout, for instance, or there is a learning effect. And then BA. And then BA, it is the same, but this is B, this is BA, and this is A, and this is BA. And now we have the carryover from the first period to the second period, that is now B. Okay, now how do we estimate the mean for each one of the treatments? So we typically average all those individuals receiving the treatment A. So individuals receiving treatment A are these ones and these ones. So we add the two, compute the average. So we this is the expected value for these ones, this is the expected value for these ones, and we divide by 2. So we have that the mean of the individuals receiving A depends on A and the carryover divided by 2, and the same for treatment B. So we have the carryover of A divided by 2. So treatments are aliased or confounded with carryover effect. So if the carryover is important and there is not sufficient washout, then we will have a distorted measure of the effect of A and B. Okay, so what about this ABB BAA? So we have the same kind of expected values. So for instance, let's see this one. So this is the effect of A, because it is ABB, plus an effect of the order, plus the contribution of P1, and then the contribution of B, P2, and the carryover from A, and then this is treatment B, the order, the third period, and the carryover from the previous treatment, that was B, and the same happens here. Now we compute what is the average of the treatment A. So we have A in these, and these cells, so we add the 3, and what we have is this one. So the treatment A is aliased with the effect of or the order, which typically we don't think it will be so much, and it is divided by 3, not divided by 2. And the same happens for treatment B. So with this we finish this block of multiple blocking. We have also seen Latin squares, Greek Latin squares, and also these crossover designs.